Great, thanks. So in last session we discussed about estimation. We discussed likelihood approach for estimating parameter for probability distribution and Bayesian approach as well. Today we will be looking at GMM and EM algorithm. So to get started with that, we'll first of all take a look at a data and think of different ways in which we can come up with a generative story, that is probability distribution, which generates the data. So well, goal for today is GMM, Gaussian mixture model, and EM algorithm. Okay, so well, let's say we have data. Just a second. This is our data. This is the number line we have, and here we have data. These are data points we have. As data is not just zero and ones, so we can't take Bernoulli distribution. So we have to think of a distribution which generates this data. So naturally, we can go for Gaussian distribution. Well, this is the distribution which generates the data. Well, we can say, okay, our this is our Gaussian distribution that generates the data. But what could be problem with this distribution? Anyone? What could be problem with this Gaussian distribution generating this data? Hello, are you guys there? Am I audible? Anyone? Hello, are you guys there? Hello, am I audible?
Yes, you are audible. Actually, it looks like we have that data points are three different regions, but our distribution says it is only at one at one location. It is highly clustered.
Yes. So the problem with taking a Gaussian distribution here is that points are coming from very dense region also. So well, probability that points come from this region is very less, but still points are coming from this region. That's the problem. So the problem with this generative story is that lots of points are coming from less dense region. So what could be a possible solution? So we want probability distribution which has multiple peaks. To be specific here, in this case, we want to have a probability distribution here which has three peaks. And let's look at it. So we want a distribution which is like this. Well, the diagram may not be very clear. Let me try to redraw it. Just a second. Well, we want this type of distribution to generate the data. Well, and this is what, as you can see here, you have three Gaussian distributions here. So this is what? This is Gaussian mixture model. So this is called mixture of Gaussian. So now the data here is generated in two steps. In the first step, so let me write the generative story for this. Generative story here. So in step one, we choose the mixture from which the point is getting generated. Well, you have three Gaussian distributions here. You have to select from where your point is getting generated. A given point is getting generated. So, so we have to pick which mixture a data point comes from. And for this, what you have, well, let's say you have k mixtures. Okay, so from 1 to k, you have mixtures, and mixture indicators you have ZIs. So for point x1, if z1 is equal to 1, that means the point comes from mixture 1. Just a second, I'll be back in few seconds. So in the first step, we are picking the mixture from where data is coming from. And for each data point, we have cluster indicators here. Sorry, not cluster indicator, my bad, mixture indicator. So, well, you have when you have n points, you have z1 to zn, and they will take value equal to the mixture which they belong to. So this zi will belong to set which has 1 to n numbers. And well, for any given point I in the data, the mixture indicator will be equal to some L, let's say. L is some number, and you will have some probability associated with it, pi L. So a given data point, a given data point can come from this mixture with some probability, this mixture with some probability, and this mixture with some probability. So let's say it comes from this mixture with probability 0.5, this mixture with probability 0.25, and this mixture with probability 0.25. So that's what is meaning of this here. So this means that if you sum all pi's, that will give you, that will be equal to 1 simply because of probability. So on summing your, for a given point, if you sum all the pi's, so well, when you have I equal to 1 here, this is probability that this is probability that some point belongs to first cluster, first mixture. When I is equal to k, that means uh, data point belong, what is the probability that data point belongs to kth mixture here. So sum of all that will be equal to 1, and each pi value will be between 0 and 1, and this is true for all i's. And after this, after you have chosen the mixture which is generating this data, then simply you generate the data as per the normal distribution. So generate your xi data from normal distribution mu zi with mean mu zi and variance sigma square zi. So this is your generative story here. So is this clear? Hello? Is the generative story here clear? Hello?
Yes, sir.
Okay, let's move ahead. So now, well, what's the point of this? So we, what we want to do here, we want to estimate the unknown parameters here in this generative story. So this is your probabilistic model here, that is a probability distribution which generates data. You want to estimate the unknown parameters for this probability distribution. So the question is, how many unknown parameters we have here? So the question is, how many unknown we have here? That's the question. Well, so you have pi's, correct? Well, three, you're saying. Okay, let's look at that. Three for each data point, you can say. No, let's look at that carefully. So now you have pi's. Yes, just a second. So now we are looking at how many unknown parameters we have here. So you have pi's well, let's say pi vector has all the pi's. So corresponding to each mixture, you will have value of pi. So for mixture 1, you have pi 1. For mixture 2, you have pi 2. And if you have k mixtures, you have k pi's corresponding to the probability. And for each mixture, you will have parameters for normal distribution. That is mu you will have, and you will have sigma square. So total, you have, well, first of all, for each pair of uh, for each normal distribution, you have two parameters, and you have k normal distribution, so you have 2k of this parameter, 2k coming from mean and variance of normal distributions. And now you have k minus 1 coming from pi's. And why k minus 1? Because here you have you have k pi's, and sum of all k pi values will be equal to 1. So last one we can simply find by subtracting the sum of first k minus 1 from 1. So that's why we have k minus 1 here. So this comes out to be 3k minus 1. So this many unknown parameters you have here. Is that clear? Hello? Any doubts so far? Anyone?
No, sir.
Great. So now let's look at maximum likelihood for this GMM. So we'll look at maximum likelihood for GMM. So, well, your likelihood function will take in all the data points and candidate parameter. So here, first of all, you will have means of all normal distribution, and you have k normal distributions. So mu1 to mu k. Then you'll have sigmas, that is variance for normal distributions. You have k variances, and then you have k pi's, pi 1 to pi k. And you have data points, that is you have n data points. So you have x1 to xn data points, and your likelihood function will give you the probability of generating this data given these are the unknown parameters. So that will be equal to product over I equal to 1 to n of PDF for this Gaussian mixture. You have PDF of GMM generating your ith point. I'll simply copy this from here. Well, now for any given point, let's say we are talking about this x3. This x3 can obviously come from this mixture, this normal distribution. It has high density of coming from this, whereas it can also come from this normal distribution as well as this normal distribution. It is also, that's also possible. So for each mixture, you will have a value of pi. So for point x3, for point x3, write it here. So for x3, the point, the overall probability of x3 being generated will be equal to pi 1 into, well, when it is coming from first normal distribution, then let me write f1 x3. This is the probability that it is getting generated from this one, this normal distribution. Similarly, for rest 2, you will have pi 2 into f2 x3 plus pi 3 into f3 x3. So this is how a point gets generated. So when we apply this, when we use this logic here, then what we get? So this product remains here, I from 1 to n, and now each point can be generated by k mixtures. So summation k from 1 to small k. Let me denote k 1 to k, as it can come from k mixtures with some probability, and after that for each you multiply with their corresponding density. So xi being generated from their density. So is this clear? Hello? Is this line clear? Hello? Great. So, well, now what? How can we exploit this? So now, well, if we take log now, so I'm not to denote all these, to denote all these, will be using theta. So now your likelihood function with all these points and all the parameters, on putting the PDF formula of Gaussian, it becomes product over I equal to 1 to n, then summation from small k equal to 1 to k then pi k for corresponding to each mixture, and now the PDF for normal distribution, which is e raised to the power minus xi minus mu k whole square divided by 2 sigma k square, and this thing divided by root over 2 pi into sigma k. Well, this is your log likelihood function. Sorry, likelihood function. So after this, what we do, we take log, and on taking log, what you get? So your log likelihood, well, on taking log, this product over I equal to 1 to k will be converted into summation. So this will be equal to summation I from 1 to n, then summation, sorry, after this you have log. Once you take log over it, this value comes out and becomes summation, and you are left with all this inside. So inside log you have the same thing, so I'll simply copy it. Inside log you have the same thing. So now the problem here is that we have summation inside log, and this is not possible to solve analytically. Well, so we can't simply differentiate it, put it equal to 0 and find the value of unknown parameters. That's the issue here. So we need to come up with some algorithm to solve this. So is the setup so far clear to you all? Hello?
Yes, sir, it's clear.
So now what we do? So for this, we'll be using Jensen's inequality, and for that, let's have a quick detour of convex and concave functions. So quick revision of concave and convex function. Convex and concave function. Well, so when we talk about anyone who remembers concave and convex function? So let's say we have a graph, this, let's say number, this is fine. So for any function, let's say this is a function, okay, and we have 2 points A and B. This is point A, this is point B. Okay, and this right here is the function's value at point A, and this right here is function's value at point B. So if the function is such that The linear interpolation, the linear interpolation. Okay, let me take point B farther from here for better diagram. Just a second. So point B, let's say here. This is the point B for us. Function's value at point B, function's value at point A. Now the linear interpolation of the 2 points is this. Okay, let me redraw it. This is the linear interpolation. So a function such that the function's value between any 2 points A and B is less than the linear interpolation between the 2 points. When this holds, then the function is convex function. So mathematically, this is, well, right here, let's say you have A plus B by 2. So function's value at A plus B by 2, when that is less than the linear interpolation. So this point right here is A plus B by 2, and this point is what? The y value for this point will be function's value at A plus B by 2. And here you will have one point, which will be midpoint of this, and y value of this is what? F of A plus F of B by 2. And when your F of A plus B by 2 is less than equal to F of A plus F of B by 2, when this holds, then the function is convex function. Okay, so is this clear? This convex function here, and this holds for all A and B. This holds for all A and B. So this is what convex function is, and concave would be opposite. Well, for concave you will have graph like this. So just a second. Okay, a graph like this. So linear interpolation here for any 2 points A and B will be below the graph. So here F of A plus B by 2 will be greater than equal to F of A plus F of B by 2. And this function is what? This is concave. This is a concave function. So is the idea of concave and convex function clear? Hello? Hello, is that clear?
Yes.
Yes. Yes.
Now, well, we talked about convex function, concave function. Is there any function which is both concave and convex? Well, the answer is yes, because here, as you can see, in both the inequalities, you have equal to. Here you have less than equal to, here you have greater than equal to. So, a function which satisfies equality will be both concave and convex. And what function is that? Anyone?
Linear.
Correct. So, linear function satisfies both concavity and convexity. So, linear function is both concave and convex. And what function is neither concave or convex? Well, a function like this, you can say. At here, it is what? It is a concave at this point. But here, as you continue, it becomes convex. So it is neither concave nor convex. Neither concave nor convex. Now the question is, well, how this all is beneficial to us? Well, it is beneficial to us, and let's see how. So, when let's say we are talking about concave functions, okay? So, well, what's the inequality? Uh, as per the function definition, concave function definition, it is f of a plus b by 2, right? So that can be written as 1 by 2 times a plus 1 by 2 times b. And this is less than equal to 1 by 2 times f of a plus 1 by 2 times f of b. Well, it's the same thing. We have not done anything different. So, as per this definition, the graph is what? Like this. So, an important thing to notice here is that this is not true only for point a plus b by 2. This holds for all the points between a and b. Correct? This is a, this is b. So, this holds for all points between from a to b, you can say. So, if we move here in this interval, this also holds. So to move here, what we can do, we can change the value of scalar here. So when we want to move in this interval, we can set this scalar to lambda. So in that case, the inequality becomes lambda times a plus 1 minus lambda times b. This is less than equal to lambda times f of a plus 1 minus lambda times f of b. And here, important thing is that your lambda belongs to interval 0 to 1. So by this inequality, you are stating this for any point in the interval a to b. By changing the value of lambda, you can move in this interval. So is this clear? Hello, is this clear?
Okay. Yes,
Hello.
it's clear.
Okay. So now we can extend the idea. So here you have just a two points a b. We can extend this idea to higher dimension, and this becomes what? F of. So I'll just write extending the idea. Extending the idea. On extending the idea, what you get? F of lambda 1 a1 plus lambda 2 a2 plus summation up to lambda k ak, and this will be greater than, well, just a second, well, here we have a mistake. For concave, when we are talking about, this will be greater than, equal to, yes. So this will be this f of lambda 1 a1 plus lambda 2 a2 up to lambda k ak. This will be greater than equal to lambda 1 f of a1 plus lambda 2 f of a2 sum up to lambda k f of ak. And this right here is called Jensen's inequality. So a compact way of writing this is by using summation. So f of summation from k equal to 1 to k lambda k ak is greater than equal to summation where k from 1 to k lambda k f of ak. This is called your Jensen's inequality. And this we will be using for solving the log likelihood. Well, what's the geometric interpretation of this? In 2D we have looked at this. We can look at 3D. So let's say you have this is your plane, and the function is like this. This is function. A 3D, you can think of it as a 3D dome. The diagram may not be very good here. So let me read, right? Okay. So this is the function, and the function value will be always greater than linear interpolation of any 3 points in 3D. So these are the 3 points. So you can move anywhere, and the linear interpolation will always be lesser than function's value. This is the linear interpolation, and this is always less than the function's value. The graph of the function move is above this right here, if you can imagine this. So is this clear? Hello. Is Jensen's inequality clear? Hello, am I audible?
Yes,
Yes, sir.
sir. Yes, sir.
So this is your Jensen's inequality. Now, what's the use of this? So good thing here is that your log function is concave function. So we can exploit Jensen's inequality here. So let's use our Jensen's inequality in solving log likelihood. So what is your log likelihood? So your log of likelihood function is equal to summation I from 1 to n log over summation from k equal to 1 to capital K, and inside summation you have pi k e raised to the power minus xi minus mu k whole square divided by 2 sigma k square. Well, this is nothing but part of normal distribution into 1 by root over 2 pi multiplied with sigma k. The log likelihood here. So now how can we use Jensen's here? So we have to make this look like your left hand side from Jensen's inequality. So how can we do that? So here, as you can see, you have function of something, and inside function we have summation. So summation we do have. Okay, this is your function. This is okay, and inside summation you have some value, but you also have pi k's. So we have to somehow introduce here pi k. So what we will do, we will here multiply by pi ki and divide by pi ki. That's what we will do here. So essentially we are not doing anything new, right? We are multiplying by same thing and dividing by the same thing, though, so the function remains the same. We are just manipulating it a little to make it of the form of left hand side of Jensen's inequality. So this is equal to summation I from 1 to n log summation cap k from 1 to capital K. Now here you have lambda ki. So for each point here, for each I here, you have k lambdas. So for I equal to 1, you will have k lambdas. For I equal to 2, you have k lambdas. For all n data points, you will have k different lambdas. And then you have some numerical value here, which is given by this. So I'll simply copy it. Well, and this thing is divided by lambda ki. So we'll divide this entire thing by lambda ki. So now this is of the form of left hand side of Jensen's inequality. This right here is your function. Inside it, you have summation over k from 1 to k, and you have pi k's, and then you have some numerical value here. This is your ak. So now from Jensen's inequality, this is lower bounded by this value. So this what we will call the function that lower bounds this the log likelihood, that we will call modified log likelihood. So your log likelihood function is greater than equal to this modified log likelihood, which has different mu's, sigmas, and lambdas and pi's. And this modified log likelihood is equal to, well, on using Jensen's, this is equal to summation I from 1 to n. Then summation again you have for each value of I, you have summation over values of k from 1 to capital K. Then you have lambda ki log of the same thing, this numerical value here. So simply I'll copy it. I will copy this part. Log of this.
Sir, I am not getting it. Why, what is the use of lambda ik?
Yeah, we'll come on that. So as of now, we have introduced this lambda ik to use Jensen's inequality. Well, without this lambda ik term, you cannot use Jensen's inequality here, right?
Yes, sir.
Correct. So as of now, the reason why we have introduced this lambda ik is to exploit Jensen's inequality and come to this modified log likelihood function, because this log likelihood function, this we cannot solve. Is that clear?
Yes, sir.
Okay, and what exactly is lambda ik, that we will discuss. Well, now here the good thing about this function, modified log likelihood function, is that we can find the parameters from this. That's the good part. So here one important thing is that the modified log likelihood gives you a lower bound for actual log likelihood, for true log likelihood function. For your at theta, and by theta what we mean all your mu's, mu1 to mu k, your all your sigmas, sigma 1 square to sigma k square, and all your pi's from pi 1 to pi k. All this by theta will move. And for any choice of lambda, and by lambda what we mean? Well, for each data point you have k lambdas. For point I equal to 1, you have lambda 1, 2 lambda k. Similarly, for all points you have values of lambdas. It gives you lower bound on true log likelihood. That's the important point here. And well, how can we find the value of parameters from this modified log likelihood? So that's the question. So the question is, how can we find theta and lambda from modified log likelihood? So answer to this is, we can, if we fix the value of lambda, if we fix the value of lambda, we can easily find the value of theta, and if we fix the value of if we fix the value of theta, we can find lambda. That's how we will approach this. So is the idea here clear? So far, any doubt?
Sir, both are dependent on each other, na?
Yes.
Yes, sir. Here, the pi is the probability and the lambda is the constant, right?
No, at this, in the modified log likelihood, in the likelihood function, what are they? They are unknown parameters, right? We are saying from the modified log likelihood function, we can find the value of lambda if we fix thetas. And what is theta? By theta we mean all the mu's, all the sigma squares, all the pi's. If we fix all of them, we can find the value of lambdas. And if we fix lambda,
Okay.
you can find value of all mu's, all sigmas, sigma squares, and all pi's. So now let's proceed. Okay, again, I'll ask. Any doubts so far? Anyone else? Feel free to ask.
No, sir.
Okay, let's continue. So let's fix lambda and find the value of theta. Okay. So fix lambda and maximize over theta. So we want to find theta. By theta we mean all mu's, all sigma squares, all pi's, such that this function is maximum. This function is maximized. I will simply copy this. Want to find maximizer of this. So here we are fixing the value of lambdas. Well, when we fix the value of lambda, what we get, that's the question. On fixing the value of lambda, you after that what you do? You differentiate it to find the value of mu, you differentiate it with respect to mu. So you get the value of mu, and after that, same thing you will do for sigma. But when we talk about pi's, so that's unconstrained, that's constrained optimization problem. So let's look at that. So let's look at the results we get. So on taking derivative with respect to mu sigma, we get, so you get the optimal, sorry, not the optimal, you get the mu hat mml. So for mixture, for kth mixture, this value is equal to summation I from 1 to n lambda ki xi divided by summation I from 1 to n lambda ki. Well, this is what? This is kind of mean of that particular mixture. And the sigma square, sigma k square hat is equal to summation I from 1 to n lambda ki, and after this you have term from your variance xi minus your mean of that particular mixture of kth mixture, then square this and divide it by summation from I equal to 1 to n of lambda ki. So is this clear? Hello? Any question from this? Hello?
No, sir.
Well, you can look at this as kind of weighted mean, you can say. Okay, this is the weight. You have weight corresponding to each point belonging to that mixture. Then you have the weighted sum here. Then you divide by the sum of weights. And here also you have this term from variance, and here you have weight, and here you divide by sum of the weight. So it's like weighted mean, and this is what? This is weighted variance, you can say. So these particular these are what? This is mean for kth mixture. This is variance for kth mixture. And now we talk about pi's. So when we are maximizing the function for values of pi. This right here is not straightforward optimization problem. This is constraint optimization problem. So this will be solved using, we haven't discussed Lagrangian in the course. Later in weeks of SVM, it will be discussed in week 10, I believe. So as of now, we just have to look at the result. So summation k from 1 to capital K, lambda ki log pi k. And here the constraint is that summation of all the pi's is equal to 1. And value of all the pi's is between 0 and 1. So this will be solved using this will be solved using Lagrangian multiplier. You may have covered it in MLF. Lagrange multipliers. So the result is important here, and the result of pi is what? The pi k hat is summation from I equal to 1 to n of lambda ki divided by n. Well, this is what if all the points belong to a, only one mixture, then this is what? This is nothing but, okay, this can be interpreted as the proportion of points going to R, or you can say coming from mixture K. So these formulas are very important here. This one formula here, this formula for mu k, and this for mu k sigma square hat. Yes, so any problem here? Hello?
No, sir.
Okay. Now these three we get when we fix the value of lambda and maximize over theta. What will we get when we fix the value? So fix the value theta and maximize lambda. So what we get then? So in that case, well, let's again write the value of modified log likelihood. What's your modified log likelihood? It is summation I from 1 to n, and for each I value you have summation k from 1 to capital K, and you have lambda ki, then log of pi k you have, then e raised to the power minus xi minus mu k this whole square divided by 2 sigma k square, and this whole thing multiplied with 1 by root 2 pi sigma k square, and this whole thing is divided by lambda ki.
Sigma, sigma k
Well,
only, sir.
now,
From the root.
where?
This one.
Okay, yes,
1
here.
by.
Right. Yes, thanks for the correction. And now once you take log, what happens? So now we'll use the property of log simply. So this is summation I from 1 to n, then summation k from 1 to capital K. Then what you do, you take log of this. So this is one term. So simply you have log of this multiplied with lambda ki. So this is lambda ki log of this term. Similarly, once you take log on this, log of this term, so this entire thing in power comes forward, and you have just log of u which is equal to 1. So you are left with this term. Okay, and then here also, once you have log of this, so this can be written as this whole raised to the power minus 1, and this comes in numerator, then your minus 1 from property of log comes forward, and you are left with log of this. And similarly for this also. So directly, I mean, we can write log of one constant term, because here you don't have lambda i's, and here your thetas are treated as constants. So your theta of aik minus lambda ki, then log of lambda ki. And here your aik is what? It's the terms with all the constant here, as theta is treated as constant. So lam it is pi k e raised to the power minus xi minus mu k whole square divided by 2 sigma a square into 1 by root 2 pi into sigma k. And here once we, so the optimization problem here, what it is? So for any I, the optimization problem is maximize over values of lambda. So maximize over value of I. So you have lambda 1 I to lambda k I. These are the values you have to find, maximizers, and the function is summation I from 1 to k. As we are taking single I, so here this is the function we are left with. I from 1 to k lambda ki log of constants minus lambda ki log lambda ki. Then here also you have constraint. The constraint we have is that summation of all the lambdas from 1 to k equal to 1, and all the values of all the lambdas will be between 0 and 1, including 0 and 1. So on solving this again with Lagrange multiplier, what we get, the result is, so lambda ki using maximum likelihood here will be equal to 1 by root over 2 pi sigma k into e raised to the power minus xi minus mu k whole square by 2 sigma k square. This is the first term, and this is multiplied with pi k, and this is divided by summation from, let's say, not I, L equal to 1 to k summation over 1 by root 2 pi sigma k, again e raised to the power minus xi minus mu k
Sir, here XI, yeah, XL.
where here
Y-
okay,
Yes.
here you will have xi because this is the I we have fixed, right?
Okay.
Here for a given I you have different values of lambda, right? That's why we are here summing over it.
Okay.
Don't, this is a fixed point we are talking about for any I.
Yes, I got it.
And now divided by root sigma square L, and this multiplied with again pi L. So and now this is the final value of lambda ki, and then now let's look at its interpretation. What is meaning of all this? Okay, so well, if we compare this, this is actually this is actually equal to probability that your ith point belong to mixture K given the point. So this lambda ik is that. So for any point I, you have k values of lambda, right? Okay, so let's talk about k values of lambda. So lambda 1 you have, then lambda 2 up to lambda k. So this is what, this is the probability that the point belongs to first mixture. This is the probability that point belongs to second mixture. Your ith point belongs to second mixture. This is the probability that your ith point belongs to kth mixture. So that's why for each point you have k values of lambdas. Okay, so this is the probability of your ith point belonging to some mixture given the point. So is it clear what is lambda ki now? Hello?
Yes, sir.
And the solution you get is equivalent to what you would get from Bayes rule. So this first term right here is probability of this point xi given that the ith point belongs to cluster K. And this pi k is what? Pi k is probability of your point. Is this is the probability that your point belongs to kth cluster. That is, this is probability that zi is equal to k, and this is divided by probability of generating this point. And this point can be generated in k ways, right? This could be in cluster one, sorry, this could be in mixture one, this could be in mixture two. So that's why we are summing over k terms here. Is that clear? Hello?
Yes, sir.
Yes, so this interpretation is also very important. So this is your analytical solution for this. So now we have to come up with an algorithm to find this. So the algorithm for this is EM algorithm, your expectation maximization algorithm. So before that, any doubts so far? Hello, any doubts so far? Anyone?
No, sir. No, sir.
Okay. So now, well, now we'll look at the algorithm for solving this. So EM algorithm, expectation maximization algorithm. So here, what we do, we initialize values of theta. So first of all, initialize value of theta, that is, this zero denotes zeroth iteration, and by theta we mean all the mu's, all the mu's, all the sigmas, and all the pi's. Okay, and until convergence, and for convergence, what we check the difference between the, so until convergence, for convergence we'll check the absolute difference between the thetas you have, by that all the values we have at t plus 1 iteration and the last iteration. Just a second, I'll be back in few seconds. Hello? Yes. So for convergence, what we'll do, we'll check the absolute difference between value of theta at t plus 1 iteration with the previous value of theta at the previous iteration. So if the difference is less than some very small number, then it means that we have achieved convergence. And in each step, what we do, you find the value of. So one important thing here is that what we discussed in finding this. So we discussed that we can find the value of theta once we fix the value of lambda, and we can find the value of lambda once we fix the value of theta. So here what we are doing, actually, when we solve this, we are not getting the value, right? We are getting expression to find the value. And for finding the exact value, we must know the value of, well, to find the value of theta, we must exactly know the value of lambda. And to find the value of lambda, we must exactly know the value of theta. So this algorithm initialize random value of theta, okay, some value of theta. And after that, what it does, once you have fixed the value of theta, you find the value of lambda. So as discussed above, you find the value of, sorry, you find the value of lambda once you have fixed the value of theta. Okay, so we find the maximizer of modified log likelihood, which has theta of tth iteration, and the lambda we'll get will be of t plus 1th iteration. And once we find the value of lambda, what we do, well, as we randomly chose the value of theta, what we will do now, we now will fix this lambda and find the value of theta. So we find the value of theta is argmax of theta, and objective function is modified log likelihood. Here we are finding the value of theta and we have fixed the value of lambda. So once we do this, now again we'll fix the value of theta and find the value of lambda, and we'll keep on doing this until convergence. So after convergence, you'll get the appropriate value of theta and lambda. And this step of finding lambda is called expectation step, and this is called maximization step. Maximization step, and this is expectation step. Okay, so this was your algorithm for finding the value of theta and lambda. So any problem in algorithm? Hello? Hello?
No, sir.
Okay, and why do we actually need an algorithm? Is that clear? Because we cannot find the exact value of theta and lambda, correct? So we have to first of all initialize value of theta. For that, find the value of lambda and continue this for few iterations until convergence. So is that clear?
Yes, sir.
Okay. So what is this EM algorithm exactly doing? So this, from this EL algorithm, we can do clustering also, and for that I would like to show you guys an animations. Let me see if I can load it on the note, one note, insert. Okay, I can't load this, so I'll show you just a second. I'll open another window. Is the screen visible? Hello, is my screen visible? Hello.
Yes.
So this is how your EM algorithm do clustering. Okay, so on one side you have soft clustering, and why, what do we mean by soft clustering? That here you don't put any point directly. Well, here you can see points colored in different way, but all points have some probability of going in some mixture. Your any given point has probability of going in purple cluster, blue cluster, as well as orange cluster. And you can make it hard clustering by saying, okay, one which has highest probability, we'll assign the point to that particular mixture. And as you can see here you have three different Gaussian mixtures from where your data is getting generated. So is the animation clear?
Yes.
So a few more points left that we'll discuss. So important points are, so from, you can write important points. Is my screen visible? Is my screen visible? Hello.
Yes, yes.
Yes.
So now from your EM algorithm, with help of your EM algorithm, you can do soft clustering. With EM algorithm, we can do soft clustering. And what do we mean by that? All points will have probability of going into some mixture. Let's say if you have three mixtures, you'll have three different probabilities of that point going into the respective mixture. And you can convert this into hard clustering. And what this EM algorithm, how this EM algorithm is better than your k-means algorithm. Let's say your data, let's say data is coming from, let's say the data is coming from the below model. And here the underlying probabilistic model of generating data has two Gaussian mixtures, one like this and the other like this. I'll take different color. So the other one is like this. So your k-means will have difficulty in clustering these points, okay? But as so your k means will not be able to cluster points properly. But as you are as you are using variance in your EM algorithm, it will be able to cluster these points of these region properly. But as we are using variance in EM algorithm, or by that we mean we actually use variance in the modified log likelihood function of GMM, or I should say GMM here, GMM, or you can write EM algorithm, no difference. In EM algorithm, it can cluster points belonging to intersection region properly. And the other important part is that EM algorithm does not cluster your points based on Voronoi region. So the next important point is that EM algorithm need not to be using regions. Yes. So these are some important points. And now graphically, let's look at what is your EM algorithm doing. So when we look at the graph of your modified, sorry, your likelihood, GMM likelihood. Okay. Any doubts so far in what we have discussed? In the meantime, I'll draw the graph. Any doubt? Hello?
No, sir, it's fine.
Okay. So now let's say the graph of likelihood of GMM is like this. So your modified log likelihood has like, it is kind of using Jensen's, so it is graph here in this entire thing. So it will be able to find this maximizer of this one. And whereas when you talk about your EM algorithm, it's able to find local maximizer of the original function, like this. Depending upon your initial value, you may find this local maxima, or you may find the true solution, which is not very likely. You are most likely to find some local minima for the actual true function. So GM converges to your EM algorithm EM algorithm EM algorithm converges to local maximum. Local maximum. Your log likelihood function. So, is it clear? Hello. So that was it for week 4. Any doubts so far? Hello.
No, sir, it's fine.
Anyone else? Any doubt? So here we have entire annotation for week 4. I'll just share that in chat. And if anyone has doubt, feel free to ask. And in next session, we'll be covering PYQs of week 3 and 4. We have already covered PYQs of week 1, 2. If you haven't looked at it, please do check it out on YouTube. I have shared a notes in chat. So thanks for joining the session. We'll again meet on Saturday. Sorry, not Saturday, Wednesday.
Thank you.
Thank you.
Thank you, sir.